Hello everyone, my name is Omar Alqerm and today I'll be speaking about the real world application, the search and ranking, especially in the power of web. So now we'll be talking about the real search ranking. The outline here in our presentation will be having three sections. First, we will describe the problem and why a search engine is a hard and why does it matters, and we will explain how do we model the web as a directed graph, and we'll be talking at the end. The third one is how does the ranking algorithm separates a useful search engine from a useless one. So the problem description. Why does the ranking matters? Think about it like when we type a query into a Google, you are searching through a billions of search engine pages, but Google returns the result of what you are looking for. And the top results always that shows you is the results of what you want. How that how do you decide what's on page one and what's on page 1000? This is the core problem. This is our whole problem. We need to know how does it show you the results that you're looking for. The ranking problem algorithm is what separates a useful engine from never to go on the first page by ranking it through 1 through 10. So it makes a difference between a website thriving or being invisible. Here's the challenges. How to measure the page importance. So this challenge, we need to define the importance for the web page. How is it done? If you search, let's say if we search on Google graph theory, pages that mentions the graph theory will be showing, but many times should rank higher, but this breaks down into immediately. So websites owners quickly learn to spam their pages often to return their pages often on the top as it comes in a hidden keywords. So stuffed into meta tags or represented into hundreds of times invisibly, the results were terrible. So we needed a fundamental different signal. So the key insight that led into the page rank was treat the web as great as the hyperlinks, so it can be shown. Here now we'll be talking about the page rank brief history. In the 1990s, the search engines like the Alta Vista and Lycos, this was popular, but the results were notoriously bad. Why? Since spammers gained their keyword exponentially, but the search quality was falling. In 1998, there was two PhD students, sorry, they were graduated from Stanford, and another PhD student whose name is Sergey Brin published a paper called The Anatomy of a Large-Scale Hypertextual Web Search Engine. When they created this, if a researcher paper is cited by 100 others, it's probably most important than the other that's cited by two. So here we can say it was how does the pages being ranked? They used to let spammers to keep on spamming their page or something, so it can be on the top results. Now we need to talk about the graph modeling and the web as a graph, sorry. Now let's talk about the graph modeling. The entire worldwide can be represented into a directed graph. Each web page is a node, and when a page A has a hyperlink, let's say, that takes you to page B, so this has a directed graph as it takes you from one point to another point, and it says the direction from where to where. So this can be a directed graph from A to B. The direction matters. Why? Since pointing to B means A is endorsing the reference of B. The asymmetry is the key of measuring the authority. We need now to talk about an example. The Wikipedia page on a graph theory has thousands of page insights linking together, but it does not link back all of them. So the real world graph has about 5 billion nodes and a 10 of trillions vertices, edges, making it one of the largest graphs ever analyzed computationally. Now we'll see the example. Here is, as we have a 5 pages, 7 links. Here's the nodes, which are the pages. We have 5 pages, which is A, B, C, D, and the directed edges from A to B, A to C, B to D, B to E, C to B, C to D, and then D to E. So let's see this example. We have 5 web pages, which is A, B, C, D, and the 7 links. The links between them are formed by a directed graph. So page A links to both B and C, and the same thing goes to B. It's linked to D and E as a directed, and C is connected to B and D is connected, links to E. Notice that the pages B has 2 incoming links exactly, which is D and E. So, but there is no an outgoing links. So this is called a dangling node or a sink. This, when you compute a page bank, the structure tell us that is B and D are important because B and D are important because multiple pages are engrossed with them. So we will use them in the page bank walkthrough. But when an incoming links but no an outgoing links, this is called node, dangling node or sink. Now we need to talk about the in-degree and out-degree measurement authority. In-degree and out-degree are fundamental graph properties. So in-degree is the number of edges pointing into the pages, V. Out-degree, the number of edges going out from the page, B. So let's say now the page making a route, the starting point, and page B has in-degree 2. So both A and C have to be pointed to page A. If they are into page A, so it is in degree. If it's coming out, so this is an out degree. A link from a New York Times homepage should carry more than weight a link from a personal blog with 3 visitors. The page rank solves this by moving it recursive. Your importance depends on the importance of the pages that links to you and divided on how many pages they link into. Now the page bank Brin page in 1998. What is a page bank? A page bank is the algorithm that transformed the web search of Larry and Sergey that published their landmark paper, The PageRank Citation Bringing the Order into the Web, in 1998. It started. The key insight: not all, not all links, not all votes are equal. If highly ranked page links to you, this is a stronger endorsement than if an obscure page links to you. So we talked about the page bank is a graph based on an algorithm to score the web page importance. It finds the web page importance. It was developed by 2 PhD students in 1998. They innovated on how to know if this page's page is important or not. The core principle: a link from page U to page V is a vote for V, but votes their important pages count more. Importance is computing recursively across the whole graphs. So as we said, this to creates a recursive definition importance that depends on a whole link of them. The random surfer model. The random surfer model is the most intuitive way to understand the page bank. This picture, someone randomly browsing, let's say picture, someone is randomly browsing on the web. They start on any page, but 85 of the probability they click on the link of what the page they are looking for. And with 15% probability, they get bored and jump into a completely random page. So the random surfer model, it's a way to understand the page rank, sorry. So it helps to find the search engine that you are looking for. As we can say here, the damping factor models that the probability of following a link versus getting bored. Typically value is 0.85. It was used by the two PhD students. Prevents rank sinks. When dangling nodes absorb all rank, it means like when they are, as we said here, n degree, but it's not out degree. So this is called the damping or rank sinks, dangling nodes. Probabilistic interpretation. The page rank, long run trace of a time randoms depends on page B. Pages that visited more often, this gives a higher page rank. So in the probability, how do we look? We look on the pages that are most recently visited. This gives the higher page rank, so it keeps on showing on the top pages. Here's the page rank formula, the formula that it came out by calculating it. How do they calculate each component? Breaking down each component, we have the PRV, which is the page ranks of pages V of what we are computing, we need to find. D is a standard number, 0.85, the damping factor, the probability of following this link. And we have N, which is the total number of pages in the graph. And we have 1 minus D divided by N, which is the teleportation term, like through which link did you enter this link, base rank from a random jobs. NRV, set all pages that link to V. And the PR, page rank of pages that you have links to visit to V. We have the odd degree and the normal odd degree and the sum of rank of contribution of all degree. 0.85, this is not a fixed number, but this is the probability of like how many percent does the, the person is following this link. So it's divided by 100. And now we'll go through the page rank iteration 0 to 1. Let's compute the page rank step by step here. We have 5 pages and the D is 0.85. So the teleportation base is 0.03. So when we divide it, it gives per page 0.03. In the iteration 0, we need to initialize order rank 1 to 5, which is 0.2. Then in iteration 1, we will apply the formula as page A has no coming links. So the rank drops to the teleportation term and increases by 0.01. Page B receives the rank from A. So here, as you can see in the first iteration, after the initial state, applying the page rank formula, so it claims that no page links to A. The same goes to B and C till he finds, and then we add them all together. Sorry. And here. Now we have the configurants and the final ranking. After repeating this computation, the values gradually stabilize from by around 50 to 100 iteration on a small graphs. The graphs are covered into a fixed values. Page E ends up Page E ends up with the highest rank of about 0.248 because its terminal destination is all paths ultimately flow into it. So all paths ultimately flow into it. So the page B gave a rank less than page E. So what gives the highest rank at the end, it is the most searched engine and it comes on the top. So here page A, deeper than the importance flow. Page A has the lowest rank, which is negative 0.03, which is exactly the teleportation floor. By applying the formula, it gives 0.03. By applying the formula that we talked about, the page rank formula, we can find, and then depending on how many iteration, we can find the best search engine will be showed on Google or any Explorer. And now we'll be talking about the hubs and authorities of the HITS algorithm. HITS algorithm is a hyperlink induced topic search. It was developed by John Weinberg at Cornell in 1999. And it assigned two scores to every page, the hub score and the authority score. Let's talk here about the authorities. Authorities high authority score. Pages that contain a high authority, authoritative content are pointed by many good hubs. As we have an example, the Wikipedia article on a graph theory. The hubs of high hub score, pages that link to many quality authorities. Like this page that you're opening, it is linked with the high authorities other pages. So this is called the hub's high hub score. Curated links directories of the best resources. Example, a professor course web page linking to a research papers. Mutual reinforcement, the core idea. Good hubs point to a good authorities. These authorities are pointed by a good hubs. So for all U link that V links to, where all U is all the authorities that they all link to V. Here we'll talk about the connections of the course concepts. Connections of the concepts. Why did the page rank succeed where keyword ranking failed? There are three main reasons. First, spam resistance. Second, is the you add words to your page. First of all, we said the spam, and the third is websites that links to you is a much harder to fake a scale. So I need to repeat something about, as we said, the connection to course concepts. We have three main reasons. The first one is the spam resistance. The second is the global context. And the third one is the weighted authority. This three is how the connection depends between the course concepts. Graph traversals, BFT and DFS. Web crawlers use BFS to discover new pages by level. The DFS is used in finding the strongly connected components of the web. So both are a prerequisite for computing a page rank. So by BFS, we discover the pages next level by level. DFS is finding the strongly connected component. The graph representation, web graphs stored as an adjacency list, sparse, we have sparse and dense. Each page has a few links. Adjacency matrix representation enables matrix vector multiplication for the page rank. For n pages, transition matrix is n by n, which is billions by billions, which is never finished. So that's why we have the graph representation. Iterative algorithms. The page rank is the power of iteration on the transition matrix, where each iteration is multiplied by the formula that before a couple of minutes I have showed you. And now we have, after the course concepts, we have why graph ranking beats keyword frequency. And here, as we said, the let's summarize of what we covered today. The web can be elegantly modeled as a directed graph, billions of nodes and trillions of edges. These models enable and apply the graph algorithm, solve the ranking problem. PageRank is a genius treating hyperlinks, which is an inherently graphic heuristic idea of the keywords using the power of iteration to compute the stationary distribution of a random walk through the dual hub authority of the frameworks. And as we said, by BFS and DFS, we can find the prerequisites of the page rank, which is finding the strong connections between the uh, by uh, by the search engine pages. We can find with the BFS and DFS the strongly connected components, and we can make the search engine BFS finds out for us level by level. And here's the references that I have used for my presentation, and I hope you enjoyed the video, and thank you for listening.